Hey there, welcome back. So in this video, we're going to talk about how to evaluate limits, or I mean not limits, the sums. But in addition, sorry, we're going to talk about how, or properties of limits and of sums. Because if we want to evaluate them, we're going to have to consider how we can manipulate them. So here we go. The properties, I don't know their names, I'm just going to describe them, go like this. So let's say I have limit 5x. This is equal to 5 limit x, regardless of what's underneath the limit. The same goes for integrals. Integral 5x equals 5 integral x. Boom. And yeah, so that's the first property. Let's talk about the second property. Say you have 5x plus 9y. They're just different variables just for simplicity's sake. So you can kind of get the idea. And of course, we can interchange lim for integral. Just go and use the integral. This is equal to lim 5x plus lim 9y. And in turn, each of these can have the coefficient or the factor leave. The same goes for integrals. So integral, and whatnot. Now, they also apply to sums. So if I have a sum, I equals 1 in, and it is, I don't know, like 10xi over 3, I can take out the x. Actually, this can be n. Let's say it's n. That's where you're going to be seeing on the questions. I can do this. This turns into 10n over 3 sum I. Now, this right here is going to be the most important idea for when you are evaluating your limits. I mean, not your limits, evaluating your integrals in the Riemann sum form. This concept right here is the first step in how you convert. Okay, other than that, I think I've covered everything. Oh yeah, another property of the integral is if the b is on the bottom and the a is on the top, or the bottom value is is higher than the top one, that is essentially saying it's a negative, and then you can switch those two. In addition, when you have a to b to c, let's say I have integral a to b and then integral b to c, something, 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 something. Uh, I can combine. Oh, these have to be the same thing. The insides have to be the same. So f of x plus, this is like saying integral a to c of f of x. And of course d of x for the notation. So you can mix and match the domains. You can also subtract. So if I have d, so a to b, b to c, minus, that's a good one. Minus a to c, and this is b to d. Then we can end up, oh yeah, it's b, it has to be b to c. Yeah. So a to b, b to c, minus a to c would be 0. Because this is our domain, so domain a to b and then b to c, a to c minus domain A to C, we're essentially saying that we've removed that. We've subtracted this domain and that. So when the inside is the same, you can mix and match domains. And and you can also split up domains. So let's say we have like 0 to 10. This is equal to, oh, an f of x, equal to 0 to 5 f of x plus 5 to 10 f of x. Simple as that. So there's a tons of different ways to manipulate them. I'm pretty sure I got all of them just now. So let's move on. So how to evaluate your Riemann sum, which is the limit, the sum, and the function altogether. So I mentioned that it comes back to this. But how does this specifically help us? It's because sums have identities. This is uh, the sum of things. I can't remember what it's called. What's the name of it? Oh, frick. Grade 10. Okay. Where was I? Oh yeah. I can't remember what it was the sum of, but it is essentially the definite integral. Where did I put this? Somewhere. Where did it go? Properties. Frick, oh, here it is. Okay, the sum of something. I'm just gonna call it the sum of a linear. And then there's the sum of squares and the sum of cubes. The sum of squares and the sum of cubes. So this translates. Each of these translate into something else, which is in terms of n. So remember how there's an n here and an n here and an n here, and then there's I equals 1, I equals 1. Well, if we want, we can turn this into something, an algebraic expression that is in terms of n. I still haven't gotten my message. Okay, so what are these? The first one is going to be n plus 1 over 2. The second one is going to be n plus 1, 2n plus 1 over 6. And then the third one is going to be pretty easy. N plus 1, same as the first one over 2, but you square the entire thing. So, when you run into any of these when evaluating your Riemann sum, you can just say, oh, I'm going to replace that with this. How do you actually do that? So let's get an example Riemann sum up here on the board. Oh, excuse me. Okay. Our function is going to be y equals x cubed. Or better said, f of x equals x cubed. F of x equals x cubed from 0 to 1. So I could write my integral like this. It could be like 0 to 1 x cubed dx. This is unhelpful as of right now. Until we get to the fundamental theorem of calculus, we're not going to be able to use it. But we do have this. So we know that we're going to start lim as n approaches infinity, sum n I equals 1, change in x equal to 1 over n, and our function is going to be, since we're starting at 0, we're going to get 0 plus 1I over n, because x is going to be changing x times I, so it's just going to end up being I over n. So we can construct the inside as I over n cubed time, and this is the height, because the function times the change in x, which is going to be 1 over n. Sorry, 1 over n. Now, the tricky part is what we're about to learn. How to evaluate this. So, remember back to the properties that I just explained. We can change the inner to I cubed over n cubed times 1 over n. And then, if we combine them, we get I cubed over n to the fourth. Sum, I just use a ton of space for that. And then, from there, we can take out what is inside that is not I cubed, which would end up being 1 over n to the fourth times I cubed, which will turn into, get the, and then it's going to be 1 over n to the fourth summation I cubed. Now, this right here is something that we've already seen, which is equal to n plus 1 over 2 squared. Therefore, we can replace it like this. We get 1 over n to the fourth, well, first lim, times n plus 1 squared. And then all we have to do is evaluate our limit for n. It's as simple as that. I really hope this is a valid function. Oh wait, it is. So let's do the top. It's going to be 1 times, so n times n plus 1 squared. Square both of those. Can I do that? Yes, I can. And then that's going to be over 4. Lim, as n approaches infinity, we're going to get to that. And so this limit is going to approach infinity. Oh yeah, I forgot. 4 in the fourth. 4 into the fourth. So now what we can do is I'm going to put these together. Actually, no, I'm not. What I can do now is I can take out the coefficient, which is 1/4. So this is equal to 1/4 times n squared, n plus 1 squared, over n to the fourth. And then I can get 1/4 lim n goes to infinity, n squared, n plus 1 squared, over n to the fourth. So this is going to go to infinity, but what I have on the outside is that, and I can then apply L'Hopital's rule until I get to something. So remember, L'Hopital's rule is just taking the derivative when the limits are infinite. So this approaches infinity, and this approaches infinity. Therefore, we can do, well, first let's simplify this. So n squared plus 2n plus 1 times n squared is going to be n to the fourth plus 2n cubed plus n squared, yeah, over n to the fourth. We've got to work it out for us. So we're going to get 4n cubed plus 6n squared plus 2n. We're going to get 12n squared plus 12n plus 2. Oh yeah, this is going to be over 4n cubed, and then over 12n squared. Yeah, so these are going to go with each other because both n to the power 4. And then we're going to get 24n plus 12 over 24n. And then finally we're going to get 24 over 24. And now the limit has been evaluated to be 1. So that evaluates to 1. So it's going to be 1/4 times 1. So our Riemann sum evaluates to 1/4. And that is how you evaluate a Riemann sum. That was a bit long and tedious. I hope you can see this down here. Can you? Yes, just barely. Um, but that's the process. Uh, First, you isolate your sum. You can factor everything out to be outside the sum until you just have the I cubed remaining. And then, so this, and then you multiply the factor times the replacement, which is your identity, and then you put it back in. Uh, you evaluate the limit, usually using a L'Hopital's rule. Um, After you factor out the coefficient, uh, which you don't actually have to do, you can still leave it in, but it's simpler to factor it out. And then you just keep doing L'Hopital's rule down and down and down until you have the outer coefficient times the limit evaluated, and then you have evaluated your Riemann sum. I think that's as bad as it gets. Let me check the homework and see if there's anything harder.